Hi, this is another calculus video. This one is on something called trigonometric substitution. And I've been following James Stewart's 6th edition calculus. This is chapter 8 in that. If you're following his essential calculus, it's in chapter 6. Anyway, trigonometric substitution. This is the video in which we use a sine of theta, a times sine of theta as the substitution. I'll, Lord willing, make two other videos, one where you substitute a tangent theta, and another one where you substitute a secant theta. Okay, well, I'll be honest. When I first saw this, my thought was this is just crazy. You know, what if we plugged in a sine of theta for x? Why? Why would you plug in a sine of theta for x when you see something of the form square root of a squared minus x squared? When I first saw that, I thought, what in the heck are you doing? What is that? I mean, my reaction, and maybe your reaction, is like, what? And it's kind of an inverse substitution. Previously on substitution, we've taken like an x and we've put it into a u, going that way. But with this kind of substitution, we're going to take, say, a sine of theta, and we're going to put it into the x, which is just crazy. I was trying to think of a good analogy, but I'm not sure I have one. I thought of maybe like with u substitution, you're putting something in your car and driving somewhere. You're driving through integration to the end. And when you get to the end of it, you know, let's say you put an x square in the u, your car. Your car's a u. And you drive it through integration, and then the x squared gets out on the other side of the border. This is kind of like getting into a sine car or a tangent car. It's just weird, or maybe I don't know. But the easiest way to think of it is with u substitution, you put the x into u. With trig substitution, you put the tangent into the x, so to speak. Well, anyway, here's this might be a good place where just don't ask questions, okay? You know, if I told you, I'd have to kill you. I'm not going to explain it. Well, but it's basically Pythagorean. A squared plus b squared equals c squared, right? And so there's a relationship between this kind of a setup where you have a square root of x squared plus a squared, or a squared minus x squared, or x squared minus a squared, that particularly fits the Pythagorean situation of sine, tangent, and secant. So anyway, it works. And so, ours is not to question why. Ours is just to do or die. So just go with it if you don't follow it. So it works. So let's take this example. And this is an example in the textbook. But you can see here we have an a squared, 3 squared, minus x squared. So we have the clue. And so we're going to take a times sine of theta. So a is 9, 3 squared is 9. So we're going to take 3 sine of theta, and we're going to plug it in for x. And so, by the way, this is a step that I have often missed with this one. You need to fill in for the dx too. So what is the derivative of 3 sine of theta? Well, dx equals 3 cosine of theta d theta. Okay? So dx d theta equals 3 cosine of theta, or dx equals 3 cosine of theta d theta. Okay, so now we're going to plug these in for all the x, plug in this for all the x's, and plug in this for dx. Again, don't forget to plug in the dx, because I missed several homework problems at one point because I couldn't figure that out. All right, so when we plug in 3 sine of theta, so there's 9 minus x squared. 3 sine of theta squared is 9 sine squared of theta. Again, in a moment, you're going to see why this works. And then x squared is going to be 9 sine squared of theta. And then here's the dx. We put the dx out here. All right, that looks like a monstrosity, but the bigger they are, the harder they fall. So, for example, I'm going to be able to factor out a 9, right? 9 times 1 minus sine squared theta. Everything else is the same. Now, here's where knowing your trig identities comes in handy, because 1 minus sine squared theta is something you might remember, and it's cosine squared theta, right? So if we bring this forward to the next page, cosine squared theta substitutes for that. So now we've got 9, and that's, again, the square root of these. Square root of 9 times cosine squared theta times 3 cosine theta d theta all over 9 sine squared of theta. Okay, so let's go ahead and take the square root of that. It's going to be 3 cosine of theta, right? 3 cosine of theta. And now we're going to multiply cosine of theta times cosine of theta, and what we're going to get is, we're going to get, first of all, 3 times 3 is 9, so the 9s will cancel out. Cosine squared over sine squared is cotangent squared, right? The tangent is sine over cosine, so the cotangent is cosine over sine. So we've got that. Now, here's a formula that I don't have really well in mind. Let us pause to memorize this formula. The cotangent squared theta equals cosecant squared theta minus 1. Let's take a moment of silence to memorize that identity if you don't know it. Cosine squared theta equals cosecant squared theta minus 1. Intense memory moment. Okay, you got it? All right. So, I don't have a great mnemonic. So, ignore the triangle for now. So, we bring this forward from the previous page. So this is 2 different integrals, right? This is the same as the integral of cosecant squared theta and minus the integral of 1. Well, the integral of 1 in this context is just going to power up to a theta. And the integral of cosecant squared is apparently negative cotangent theta. Again, another moment to memorize that the integral of cosecant squared is negative cotangent of theta. All right, so now here's the problem. We need to get it back to x. We need to get out of the taxi, right? We got into this sine theta taxi, and it worked, right? I mean, nobody, it's kind of like a trick, except it's not a trick. It actually works because of triangles and circles, right? The unit circle has sines and cosines equivalents as well. So it works because of those things. But how do we get back to x? Well, this was the substitution we did, right? We did x equals 3 sine of theta. So how do we get back from theta and from cotangent to x's? Well, it takes a little practice, but it's really rather interesting. So if we divide both sides by 3, we've got sine of theta equals x over 3. Well, let's say that this is theta, right? Let's say that this angle right here is theta. Then what is sine? Sine is the opposite over the hypotenuse, right? Opposite over the hypotenuse. Look, opposite over the hypotenuse. we can express x in terms of the sine of theta, because and get back. We're going back to x. We're finding our way back to x. So what about this side? What is this side going to be? Well, a squared plus b squared equals c squared. So x squared plus whatever this is equals 9 squared. Well, if we do a little algebra, what we'll find is that this side is the square root of 9 minus x. So if you x squared plus this squared equals 9, it all works out. So let me pause for a moment because I want to point out something. Very, very often when you do that, when you've done all that, you get back to what you started with, square root of 9 minus x squared. When you get to the triangle, a lot of times you're going to end up back with that original thing that you substituted in regard to. Okay, so we need to find out what cotangent is. Well, now that we've got all the sides of the triangle, what is cotangent? Well, tangent is the opposite over the adjacent. So what is cotangent? It's the adjacent over the opposite. So negative cotangent of theta is negative square root of 9 minus x squared over x. Isn't that fun? What a fun trick. So that's what we started with. It's going to equal negative cotangent of theta is going to be this. It's going to be the adjacent over the opposite because it's cotangent, right? The cotangent is 1 over the tangent. Now, how do we get back from theta? That's a good question. How do we get back from theta? Well, theta is going to be, if we know what the sine of theta is, then theta is going to be the arc sine or the inverse sine of x over 3, right? We've just gotten the sine away by doing the arc sine of both. Arc sine of the sine is like pulling the knot and it disappears, and we're left with the arc sine. I would have preferred to say sine minus 1. That's another way to write arc sine, but it didn't come out looking real well, so I just went ahead and put arc sine. So the minus comes from that, and the theta comes from the fact that theta equals the arc sine of x over 3 plus c. Isn't that wild? Again, if it doesn't make sense, don't worry about it. Just know how to do it, and then practice. I mean, practice is what's going to make it make sense. And I'll have, I'm going to do 2 more videos. One where you're substituting in tangent theta. One where you're substituting in a secant of theta. And then a little bit later on, I'm going to do a video that'll use the sine on a magnetic field equation. That is really fun. Again, I went, what is this, when it first happened? But now it's like, that's easy. Yeah. So you can get it. You just need a little bit of time to work on it and practice.